9:05. Welcome to Algorithms, everybody. I'm Professor Kleinberg, not the Kleinberg who wrote the book, but the younger brother. But I like using his book. So this is going to be this lecture is going to be a brief intro to how the course is organized, and then a more extended intro to what the course is going to be about. Thought I would start by just visiting the website and not reading to you every single thing, which you can and should read for yourself, but a couple important messages. So this is an advanced course in algorithms. It is intended for people who have had at least CS 2100 and 2800. We will rely quite heavily on material for both of those courses. If you got an A- or better in both of them, then you have fulfilled the prerequisites. The other way to fulfill the prerequisites for 4820 is to pass each of 2100, 2800, and 3110. If you're curious what we're going to be relying upon from each of those, from 2100, we're mostly using Java. There will be some programming assignments. You'll be expected to write code in Java. From 2800, we're using nearly everything. From 3110, we're going to be assuming that you know how to do asymptotic analysis of running times, including manipulating expressions in big O notation, solving recurrences, that type of skill set. I think there's some of that in CS 2110, but you get a lot more practice with it in 3110. So if you feel shaky on any of the prerequisites, what you should do is come ideally see me face-to-face in office hours sometime this week. My office hours are written here. If you can't find a time to see me face-to-face, just write to me, and we can have a conversation over email about whether you have satisfied the prerequisites for taking this course. I'm aware that many of the people in 4820 are master's students who did their undergrad elsewhere. So for those types of students, it's not particularly helpful to quote to you a list of Cornell course numbers and say you're only allowed to take this course if you've taken those ones. Okay, so if you have doubts about whether the courses you've taken are equivalent to the ones listed as prerequisites, we should have a conversation. There's a required textbook for the course. I just got done telling you I didn't write it. I do know the person who wrote it, so if you find mistakes in the book, tell me, because they're compiling corrections for the second edition. We talked about prerequisites. There's an interesting, so there are basically four components of your grade in this course. There's going to be weekly homework assignments. The homeworks are going to come out on Thursday nights at midnight, and they'll be due a week later. You're allowed to work on the homework in groups of up to 4 people. Working in groups is recommended. In my past experience, it's one of the ways that people learn a lot from their peers in this course. We also have a veritable army of teaching assistants. There are about 30 TAs. Each of them will be holding office hours weekly. Going to their office hours or my office hours is also a great way to get firmer grounding in the material and get help with the homework. The homework assignments in this class have a reputation for being quite challenging. So it's recommended that you get an early start and don't leave it all for the final day. There's also 2 prelims and a final exam. These are evening prelims and a morning final. The morning final is on one of the last days of exam week. Sorry about that. I don't control the schedule. In a class this size, there will inevitably be time conflicts on the exams, and so makeup exams will be scheduled for each of these 3. If you're worried because you have a time conflict, you don't even need to ask me if it's possible to get a makeup exam. You can rest assured there will be makeups for all 3 of these. And we'll be using this online forum Piazza that many of you hopefully are familiar with, both for taking care of business like scheduling makeup exams, and as a question and answer forum for students to ask and answer each other's questions. The one thing that I ask you not to do on Piazza is ask or answer questions of the form, how do you solve this problem on the homework? It's fine to discuss questions like that in office hours. Piazza is not supposed to be used for directly discussing solutions to the homework. Okay, we talked about homework. Okay. There's a very important statement to be made about academic integrity, but I think I'm going to save that for when I release the first homework assignment and move on to more fun stuff. Before moving on, does anyone have any questions about how the course is going to operate? Oh, one thing I didn't talk about is the grading system in this course. You can read about it on the website. There's an interesting grading system where you can decide for yourself if it's interesting or not. There's a grading system where the percentage of your grade that comes from each component of the course is not fixed, but it's variable within some range. And then for each student, we'll weight the different components by choosing the weight vector within the specified ranges that gives you the best raw score at the end. So for example, if you're someone who slacked off on the homework and got very bad scores, but you did fine on the prelims and the exam, the coefficient of your homework grade will be only 0.15. Someone else who the homework was the best component of their work will get a coefficient of 0.25 on the homework. And unlike the past couple of times that CS 4820 has been offered, when iClickers were used both to get instant feedback and to measure participation, this semester, to tell you the truth, it's always been the case that I despise the iClicker and have never liked using it. This year, I finally decided to just get rid of the clicker questions completely. That means there won't be a participation grade for CS 4820 this year. I'm going to take a nostalgic look around the room because for many of you, I guess this might be the last time I see your face this semester. I can't resist. This is not part of the script that I planned for this lecture, but I can't resist telling you the funniest thing that happened to me last fall. Wednesday, the last week of classes, so literally like 2 days before the end of classes for the semester, I come to my office. There's a student waiting outside my office door. I've never seen this student before. And the guy says, "Professor Kleinberg, I'm here to see you. I'm a student in your networks class," which is the course that my brother was teaching last fall. This is someone who went through 13 and a half weeks of the semester and never even laid eyes on his professor, so he didn't know that he was talking to the wrong Professor Kleinberg. How did I get on that subject? Oh, right, the participation is not going to be a component of your grade. I do intend to ask questions and get people talking during these lectures. I'm just not going to pose questions to you in the form of multiple choices where everybody has to suddenly dive for their backpack where they left their clicker. So that's what I wanted to say about participation. Oh, and video note is here. So I hate, this obviously comes up in the context of telling you that participation is not a part of your grade, and now I'm telling you that there are going to be annotated videos of the lectures online. I still very much hope that many of you will come to class and participate. We'll have a much more lively semester that way, but in recognition of the fact that there are some people who do prefer not to get out of bed at 9:05 a.m. on weekdays, you do have the option of reviewing the lectures on video note. No questions? Let's talk about algorithms. So if you have done the prerequisite courses for algorithms, then you have already been exposed to many algorithms. You've seen probably at least one order n log n algorithm for sorting a list of elements of an ordered set. Can I see by show of if you've seen an n log n sorting algorithm, raise your hands. Aha. This is a majority, but not an overwhelming majority of the class. So that's a good indication that you should look in chapter, I want to say 2. It's either 2 or 3 of the textbook. Or is it 5.1? Okay, I know there's an n log n sorting algorithm in chapter 5.1. You may have seen shortest path algorithms. There's a famous algorithm called Dijkstra's algorithm. Can I see a show of hands for those who have seen Dijkstra's algorithm? Okay. There's a famous set of algorithms for searching a graph: breadth first search, depth first search. Okay. I would characterize the stage of one's education where one learns these algorithms as they're sort of presented as isolated recipes for solving a specific problem. The aim of CS 4820 is to introduce you to a general purpose set of recipes for solving almost any problem you encounter that can be efficiently solved on a computer. That's an ambitious goal, and we won't quite achieve it, but you'll be surprised how far we can get toward achieving that goal in the span of one semester. That's mostly a testament to how ignorant mankind is right now about designing algorithms, that in a single semester undergraduate course, I'm going to be able to teach you most of the known general purpose recipes for designing efficient algorithms. There's also a recipe for designing inefficient algorithms that works on almost every problem, which is brute force search. If I give you any problem that you want to solve where it's at least possible to verify that you have a correct solution once you stumble upon one, you can always just kind of blindly try out every potential solution, and by process of elimination, if there is a correct solution, you'll eventually stumble upon it and know that you got it right. In this course, we are concerned with algorithms that are significantly more efficient than brute force search. And the basic mystery that we will be addressing and that mankind is still in the process of trying to unravel is why are some problems easier to solve than brute force search and others not? Answering these questions often involves working on puzzles. I mean that both in the metaphorical sense of mathematical puzzles and in the literal sense of like assembling puzzle pieces together into a specified pattern. Because I can actually illustrate this theme of which problems are easy and which ones seem to require brute force search using examples that have to do with assembling puzzle pieces. Here's a problem that some of you may have seen before. I hope that at least a few of you have not. I'm going to draw an 8x8 chessboard with two corners removed, the upper left and lower right. And the question is, can you cover this shape with 31 non-overlapping dominoes? Does everybody know what a domino is? It's a shape consisting of two squares next to each other. It's one that hopefully is an actual rectangle if the shape recognition is working correctly. Why the number 31? Because there are 62 squares in that shape. And does anybody know the answer to this puzzle? Yes?
Yeah, I guess you cannot do that. You can color the square in this 8 by -2 thing. So every red circle is open, so is isolated by some white square. So if you count the square of pink and the square of white, you can see that the pink one is actually smaller than the white one. But each geometry must contain one pink and one red, one pink and one white. So it's not possible.
That was a great answer. Okay, I don't know what the rest of you think of that answer, but when I first saw the solution to this puzzle, this struck me as the quintessential example of an ingenious, insightful answer that, such as only a human mind would be capable of thinking of. Okay? The mystery that we are addressing in this class is the flash of insight that leads to coming up with something like, hey, let's two-color the squares of the board. Is that a process that can be efficiently simulated on a computer, or does solving puzzles like this inherently require some kind of flash of insight that can't be efficiently simulated? Well, now that you see that one of the principles for solving these domino tiling puzzles is to two-color the squares of the chessboard in alternating colors, let's test out how powerful that principle is by designing another problem that's not quite so easy to solve. So I'm going to make a board that's also missing some squares, but this one is going to be symmetrical. Oh, man. Good enough. If I alternately color the squares pink and white, you can convince yourself that there's an equal number of pink and white squares, either by counting them or by appealing to the left-right symmetry of the diagram, which if you flip it over to its mirror image, that operation interchanges the pink and white squares, and so defines a one-to-one correspondence between them. So there's no parity obstruction to covering this board with dominoes. And the question becomes, can you, oops. Can you cover this shape with non-overlapping dominoes? This one I would grade as pretty tough to answer. I'm actually just going to take a break and be quiet for a couple minutes while you think about it. If you have scrap paper, it's much easier to try doing this one with scrap paper than in your head. Don't look at me, look at your scrap paper. Does anyone think they know the answer? Yes?
I'll try.
Okay.
I'll say no.
Okay, so you're surmising no. Do you think you know the explanation?
Yeah, because if you try to, because even though there's an equal number of pink and white squares, because it's a symmetrical shape,
Yeah.
if you split it down the middle, then there's an uneven amount. And since these are two step problems, if you can't solve them like that, then you can't solve these products.
That was an excellent answer. What's your name?
Okay.
Jorge. Okay, let me transcribe Jorge's answer and give a little terminology. I spelled it correctly? Okay, so shortening a little bit what Jorge said, if you divide the figure down the middle, there are 12 pink squares on the left half of the figure, with only 11 white squares adjacent to them. In other words, if you count up the 9 white squares in the left half of the figure, as well as the 2 that are sitting just to the right of the dotted line and are also adjacent to some of the left pink squares, you get a total of 11 white. In a domino covering, every pink square needs to be covered by a domino that also covers a unique adjacent white square that's used for that domino and only that one. And so there's a pigeonhole principle violation. If you were somehow able to cover those 12 dominoes, cover those 12 pink squares using dominoes, the pigeonhole principle says that 2 of the dominoes would have to collide on the same adjacent white square. Let me define a Jorge obstruction to domino tiling. Is a set of k squares, all of the same color, in the standard 2 coloring. That have strictly fewer than k, oppositely colored neighbors. Okay. So we've just seen an easy pigeonhole principle argument. That says if a shape has a Jorge obstruction, then it has no domino tiling. A very non-trivial mathematical fact that you will learn in March is that the converse is also true. If it is impossible to tile a shape with dominoes, then the shape has a Jorge obstruction. Furthermore, there's an efficient algorithm that either finds a domino tiling or a Jorge obstruction. I would describe this state of affairs as a victory for algorithms. On the previous page of the notebook, I presented to you a couple of math problems that have ingenious, in my opinion, hard to find solutions that appear like they might require human creativity to come up with them. We now know, and you will know in a couple of months, that actually it doesn't take any human ingenuity to solve domino tiling puzzles. There is an efficient computational procedure that's always guaranteed to find the solution. And furthermore, the solution will always consist of one piece of efficiently checkable evidence if the answer is yes, and a different type of efficiently checkable evidence if the answer is no. To illustrate the subtle distinction between easy and hard computational problems, let's now talk about domino tiling. Okay, so using L-shaped, a domino is like a domino with 3 squares. An L-shaped domino is this shape or any of the 3 other rotated versions thereof. Is it possible to tile the following shape, which is going to be just an L-shaped domino scaled up by a factor of 2? Yuck. Much better. Anybody know the answer to this one? Yes? Yes, it is. Okay, I'm a mind reader, so I can also see what you're seeing in your mind. One of them nestles in the elbow there, and the other 3 surround it. Okay, you could obviously generalize the domino tiling to any other shape that you want to try covering. As in the case of domino tiling, if I make a big shape, you can spend a long time staring at it and wondering whether domino tiling is or is not possible. And unlike domino tiling, these problems are believed to be genuinely hard to solve. So domino tiling belongs to a class of problems called the NP-complete problems. one consequence of that classification, okay, so NP-complete is a term that we'll be talking about also in March. I'm actually not going to present to you the proof that Trombino tiling is NP-complete, which, as far as I know, is kind of boring and not very educational. But this is a class of problems that are believed to have no efficient algorithm to solve them. More interestingly, the complexity of all the NP-complete problems is interrelated. There are some other famous problems in this category, like the traveling salesman problem, the graph coloring problem, the Boolean satisfiability problem. And these problems are known to be at least as hard as other important problems like integer factoring, which is the putatively hard problem on which all of modern cryptography is based. So corollary of that is that if one of you discovers an efficient algorithm to solve these puzzly sounding questions about tiling shapes with Trombinos, that very same algorithm could then be applied as a subroutine in a bigger efficient algorithm that factors integers, mints bitcoins, whatever you want to do with your super powerful ultra efficient algorithm for solving all NP-complete problems in the world. Okay, so just this little change between the shape being a domino versus a trombino completely changes the complexity of the problem. That's why it's important to learn general principles for looking at mathematical problems and being able to judge whether their computational complexity is likely to be easy or hard. I finally want to mention another category of problems that represents another distinct level of hardness on the computational ladder. So for that, let's talk about tiling the infinite plane. And a puzzle to introduce this problem would be can you cover the entire plane using an infinite number of plus-shaped tiles? An illustration of what I mean by a plus-shaped tile is that. Came out uglier than I wanted. Anybody know the answer to this one? Yes?
I'm guessing no.
You're guessing no. Why are you guessing no?
Because if you have a plus-shaped tile, then on the four corners you have holes. And if you keep adding plus tiles to each other, you're still going to have holes on the corners, no matter how many times you scale it up. So even if you do an infinite number of times, there's holes on the corners.
That was my intuition at first also. It turns out that the answer is yes. So, I mean, your reasoning was non-rigorous, obviously, because it justified the wrong answer, but I had the same instinct. Let me show you what the tiling looks like. Okay, I'm going to follow your suggestion and fill in the corners. It's true that I just created more holes that I have to fill in, but amazingly, you can keep going like this, filling everything in, and never get stuck. One way of explaining what the infinite solution looks like is that the centers of the pluses form a lattice in the plane whose adjacent centers are a knight's move away from each other. Okay, so, oops, I'm still in shape mode. That's not good. So the generalized version of this question is, given a finite list of tile shapes, if we have an infinite supply of each kind, can we cover the entire plane with non-overlapping tiles? This question, unlike the previous ones, has the peculiar property that if the answer is yes, there might be no way for me to convince you that the answer is yes, because it's not possible for me to show you an infinite tiling using a finite amount of information. I sort of cheated in this case. I was able to do it because the pattern repeats. I was able to say put down an infinite lattice of pink dots in the plane where the basis of the lattice are these two knight's moves. And since we all know what it means to have an infinite repeating lattice of points in the plane, we can all agree on what the infinite tiling looks like that I'm describing with that finite sentence. The trouble with this generalized question is there are cases of this problem that have a solution, but they don't have any repeating solution. And it turns out that this problem is undecidable what that means is there is no algorithm that gives the correct answer to every possible instance of this problem. I want to emphasize that what I wrote here is no algorithm. I didn't say there's no known algorithm. We still haven't found one yet. It's a mathematical fact that no such algorithm exists. It will never be found. And you have to, if you haven't seen the topic of undecidability before, you're probably asking yourself, how can it be that we know no algorithm will ever be discovered to solve this problem? That's a mysterious proposition. How can you prove the non-existence of an algorithm to solve a problem? Okay, so that's what we will be talking about in April. And furthermore, just like with the Tromino problem, where it appeared to be a recreational mathematical puzzle, but it turns out that solving it relates to very practical things like breaking cryptography. The undecidability of this generalized tiling question is related through yet another web of interrelated problems with some very important and practical questions in program analysis. So this phenomenon of undecidability exists not just in the realm of puzzles about tiling the plane, but also in the realm of checking whether a program satisfies a property, checking whether a program will ever halt, whether it'll ever overwrite a protected segment of memory, things like that. And so the very same methods that can be used to resolve the complexity of this generalized tiling question also imply that there are many important objectives in computer science, especially in program analysis, that can never be resolved by algorithms. Okay, so that's a whirlwind tour through some of the main themes of CS 4820. When we return on Friday, I'll introduce you to the first honest-to-goodness computational problem that we'll be studying, which is called the stable matching problem. It's in section 1.1 of the book if you're interested in getting a head start.